Good morning.
Good morning, sir.
Did you see the slides or not?
Yes, sir.
Good. We are late today, so today we will talk about some of the applications because the course actually need much more time more than this. So some of the applications I will talk today using nanoscale materials and why we use nanoscale material for this. So today we will talk about the water. You know, um, you see slide number 2 now, right?
Yes, sir.
Okay. Actually, one of the main crises in the world is the water crisis, and most of the country doesn't have pure water, have some problems in this way. So the world is suffering from this, and maybe most of the country, even my country also, the United Nations have put some country will enter to water poverty by 2025. So what the people doing to solve these problems, we will show you right now. Because of the water problems, some of this is slide number 3 right now, right? Slide number 3.
Yes,
Yes,
sir.
sir.
Okay. So this is the first two pictures is from Asia actually. This is my India, some Bangladesh, maybe I don't know Pakistan or not, but yes, there's some wastewater everywhere. So the people suffering from this, and they get the water by container. There's no infrastructure even to afford the pure water. Story is very very dangerous actually. So what the people doing to do, what the government, what the social, and there's a two-way to solve the water crisis. The first way is to increase the volume of the pure water. This means you change seawater to pure water, and this process is called desalinations, and they're using renewable energy, solar cell or any energy anyway, to make electrolysis to get a pure water. I mean, to make a pure water from seawater, and this process require some sophisticated techniques like osmosis, reverse osmosis techniques, and specific membrane, and so on. And this is a little bit expensive, and only few countries have a scalable production of pure water from seawater, but the other country is still in the research stage. And the other way, and this is the mature process in most of the country, is wastewater treatment. And in this process, they will not change the quantity of pure water in the country, but they will recycle the wastewater. And there is a two-way for that. All the organic pollutant which waste the water, there's two types, even inorganic or organic. Inorganic, like heavy metals and so on, and organic, like pharmaceutical end product, fertilizer, dyes, and so on. So the people in this case they're using two-way. For heavy metals, they're using even electrochemical reductions or removal by adsorption. Electrochemical removal, electrochemical reduction, like they just use electrode, and the electrode will reduce the metal ion to metal atom on the electrode. Then they will get again, and this is a way for removal and recovery of the heavy metal from the seawater, especially the precious heavy metal like copper or something. And the main way is removal by using adsorption. But for the organic, there's a two process. The first process is to make a photodegradation, like degrade the organic pollutant to a non-toxic one, or a removal using the adsorbent. Okay. This is the general way about the water and the importance of the water. So I will skip this kind of, this is, it's not too much important, but, and also what kind of sources of water pollutions, industrial pollutions, petroleum pollutions, agricultural pollutions, sewage tank, and so on. and this is, all of you know about that, so no need for that. And even also, types of water pollutions: microbiological pollutions, chemical pollutions, organic pollutant, inorganic pollutant, physical pollutions. Also, I will not give much about that because most of you should be know about that. Um, this is, yeah. I told you last slides yesterday about when I was talking about surface area analyzer or contact room, BT method for measuring surface area. I give you some hint about nanoporous material, and this is a special class of nanomaterial, or we can say advanced nanomaterials. And it contains some, and the people right now, they're using very much in the removal of heavy metals and organic pollutant from the water using water recycling process. And this is have three class, even based on the bore dimension or bore size. If the bore size less than 2 nanometers, then we could say microporous material. If it's more between 2 and 50, then it's mesoporous material. And if it's larger than 50, then we could say macroporous materials. So why the people just start to use nanomaterials for slide number 9 now, okay? So why the people just use nanomaterial for wastewater treatment? I told you before in the beginning of this course, all the nanomaterials, most of nanomaterial already exist long time ago, but we don't know. And as all of you know, when any nanomaterials or nanoscale materials, it changes from the macro scale to nanoscale, many physical and chemical properties have been changed, and some physical properties become interesting. Sorry, slide number 9 now, right? You see, right?
Yes, sir.
Okay. So even some metal like gold, the gold is yellow, right? But when you convert to nano, you will see like blue or orange color, right? Exactly. All the the materials, when you change from macro scale or micro scale to nanoscale, most of the physical and the chemical properties have been changed, and the activity also have been changed. And one of the most important parameter change is the surface area. Surface area become much more. For example, if you have a zinc oxide, and zinc oxide, if you just take a macro scale and measure the surface area, it will be like from 10 to 20 meters cubic, maximum, maybe less than 10. But when you prepare zinc oxide nanoparticles and go and measure surface area will be 300 or maybe 350. Okay, so it changed more than 200 or 100 times. So that's because many physical properties have been changed. That's why changing to the nanoscale material, it will give you potential or tendency to use it for various or other new application with new performance. So one of for the wastewater treatment, especially when you are dealing for metal iron, for example, you wanna remove the metal iron. The metal iron is already completely dissolved. You cannot see in the water, right? And you have adsorbent, and the adsorbent is the nanoscale, right? So the chance, and first of all, you have already, if you are designing some material and the adsorbent for wastewater treatment, and you know what you are doing, then you will design some active site at the surface of the adsorbent, right? If you didn't do, then you don't know about what you're doing, right? So suppose you know what you're doing, okay? So you will functionalize some active site on the surface, right? So the active site will be distributed on the surface of the material, right? And if your material is in macro scale, this active site will not be much exposed on the surface. It will be inside, it will be somewhere, blah, 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 like this. But if you have a nanoscale material, all this active site will be abort. This one point. Second point, the chance of reactions of your nanoadsorbent with the heavy metal ion is much more, because the surface area is much higher. There is a chance to uncoiling the metal ion is much higher than if you use a macro scale material. And I told you one times before, when you have your brothers, if any one of you has brother has a five years age, okay, and he has small hand, and I give him one apple, for example, so his area, his hand will cover maybe 20 or from 10 to 20% of the apple, or maybe more, I don't know, maybe 30 or 40 of the apple. But if I give him one watermelon, then he will just take 1% of the area. So it means when you that's why when you have a nanoscale, like for example, in this one, the people used polyaniline nanofiber, and the active site here is in the backbone. Okay, if you use the polyaniline itself, then it will be entangled form. It will be macro scale. Then the backbone of the polyaniline will be crowded, so it will not be exposed to the surface, right? Because it's macro scale. But in case of polyaniline, one dimension nanomaterials, the backbone of the polyaniline will be exposed much higher. Then the chance of utilizations of the active site was much higher, and the chance to interact with the metal ion is also much higher. So another factors is the shape of the nanomaterials. Sometimes the people just use 0D, sometimes the people just use 1D, sometimes the people use 2D. So for example, shape have a significant effect in the performance of the material for wastewater treatment, for example, because it based on the shape, you can have a good performance, because when you put, for example, one dimension with this, in this study, for example, they just put some clay layers and decorated with polyaniline nanofiber, and also they used silica nanoparticle and decorated with polyaniline nanofiber. And the difference, there's a big difference between the performance of the absorption. Even the clay and the silica is inorganic materials, and also it's not have active site, but because the shape, the new nanocomposite have a different properties and have a different ability to uncoil the metal ions. Okay. Sorry. Yeah, I will just if you prepare some nanomaterials, you have to confirm with IR, I told you, and you have to do some patch experiment. I think most of you know about the patch experiment, when you have to and also for the water treatment, for example, there's whenever I'm doing Egypt and you doing in Pakistan and somebody else doing in Saudi Arabia and someone doing in Libya, whatever they're doing, the wastewater treatment procedure is the same. But the new is the adsorbent which I'm developing and you developing, right? But the same. I mean, you have to do patch experiment, and you have to change some factors, like here, for example, the factors you have to study. Otherwise, if you didn't do that, your study will not be enough. You have to do, first of all, optimize the time. The time of reactions means the time of stirring or shaking of your adsorbent with the wastewater. You have to study the adsorbent dose. You have to study the metal ion dose. You have to study the pH. You have to study the temperature effect, because the wastewater released not in normal temperature from all the industry. It released maybe temperature 30, 40. We don't know. Okay. I just give you one examples of the 0 dimensions. I mean, 1 dimension as active material, and 0 dimension and 2 dimension. But now we will give you another examples about the graphene prepared from graphite. Slide number 12, you see, right?
Yes, sir.
Okay, so this is just graphite, and this is graphene, and you know, extrapolate the graphene from graphite using ultrasonication in the presence of polyethylene glycol. Then finally decorated with polypure nanoparticles and use it for heavy metal removal. The study was very interesting because now we have. I will show you the mechanism. I think the mechanism is here or now. Yes, first of all, now we have a graphene, right? So we have to confirm that what we have is a graphene. Then the post point I told you yesterday, you have to do Raman spectroscopy, and you have to see D plus D dash, because this is the only Biggs characteristic for the extrapolations of graphene using top-down process. We use top-down process now to prepare nanomaterial. So graphene is very, Raman spectroscopy is very important, and we confirm you have graphene first of all, then, oh, sorry. And I told the people who published this paper, told they prepare some nanoparticles, polypure nanoparticle on the surface of the graphene sheets. You have to give evidence to that. You have to try to give evidence. If you didn't give evidence, then you are lucky if you publish the paper. You are lucky if you could publish the paper in good journal. You are too much lucky. You have to give evidence by microscopic techniques, okay? And you have to give evidence about the dimensions of the nanoparticles, and also the nanoparticles on the graphene sheets, okay? That's why somebody expert have to go to do TM, not just a student either, because the student he don't know what's the pictures of the material under the microscope. He don't know. So professor should care much about teaching the student how to prove this one. It's very, very important actually, because when you do the just water treatment, I told you the procedure for doing the experiment is same. All the people doing, I'm doing here. The new is the material, so you have to give much care about the material, the elucidations of the materials. Otherwise, you didn't do something new. You just repeat the other people do it, right? So this is very, very, very important. And this is just, you know, the factors I told you. You have to change time, absorbent dose, the concentration, and you have to see everything. And this is, you know, normal. And also you have to compare between polypure itself and polypure with graphene and see what is the removal efficiency. Because if the polypure itself remove some metal ion similar quantity like graphene polypyrrole, then it's not new, it's not effective. But if it's much higher, then yes, this is good. You have synergistic effect right now. That's why the polypyrrole itself have a removal efficiency around 50, 55 something, but this one, but with graphene is more than 90, 91, 92 something. And also you have to measure the selectivity of the metal ion. This one actually need much more effort and need somebody expert, because he should know about soft hard rule. They're the thumb rule, especially for water treatment. When you're gonna remove or absorb some specific metal ion, for example, like magnesium or something. In this case, you have to see what the magnesium is strong acid to which strong base, oxygen or nitrogen, and functionalize your adsorbent on the surface using that. Because when we measure selectivity, lead and magnesium, we find out the lead is 30% removal efficiency compared to magnesium. Then our material is too much selective to removal of manganese. Okay. Yeah, this is the mechanism actually. We have a polyethylene glycol, and also, I mean, when you are preparing your materials, you have to in addition to give evidence to the audience, to the readers, to the because anyway, after you publish, your paper should be read, right? Your target is to disclose some know-how you have, right? And finally, you target the people to read your paper and cite your paper. This is, and you are the intentions or the goal from your working research is to enrich the scientific society, right? Not just get the degree, nothing. So it's nothing. You will get the degree anyway. But the most more important for you is to publish some work, and some work will help the society in somehow to solve some problem, right? So you publish the work, then the people who read the work, then they will learn from you and learn from your idea, then they will continue, or they will use it, or they will just use it for different purpose. Then you enrich the society. Then you have to give much more information to the reader. Okay, so after give illustrations, you have to give the proposed mechanism and explain, highlight it with schematic diagram. Okay. Yeah, this is the kinetics. I will not give much about that because this is all of you know about that. You have to use the kinetics and thermodynamic if you measure temperatures and delta G, delta H, and so on. And at the therm you have to know based on the absorption, the interactions. If the interaction is physically or chemically, then you have to compensate in some values, and they have to draw the isotherm, see Langmuir isotherm and the Friendlich, and see what your material obey. I mean, it's going for Langmuir or Friendlich. Langmuir, if the interaction will be physical, then it will be Langmuir, and you see R square. And the Friendlich, if the interaction is chemical interactions, or you have absorption, not adsorption, because there is a difference between adsorption and absorption. Adsorption means the interaction is physically, electrostatic interaction somewhere, something like that. But absorption means there is a chemosorption occur, physical and chemical. Okay. Yeah. This is this slide number 18, right? Okay.
Yes, sir.
Okay. So, one of the most important trend of research right now is to design antimicrobial adsorbent, because the people just found, that's really fact actually, all the wastewater places is rich with microbial, or it's good environment for the growth of bacteria and fungi and so on. So one of the most important to make a dual effect or dual job is to use antimicrobial adsorbent. That's why it will inhibit the growth of the bacteria, and in the same way it will remove the waste. So this is one of the recently trend for doing that. I told you in the beginning of the lectures we have a two approach for removal of inorganic heavy metals. Inorganic heavy metal you cannot use for catalytic degradations. You have to use only removal. But one of the approach recently also have been attracted some interest to the scientists is to make electro depositions or make electroreductions. You have ions in the water, right? And that ions you need it also. You need that ions. Oh, you don't need it, doesn't matter. So after you make a removal of any heavy metals, of any pollutants, even organic or inorganic, you have to remove from the adsorbent and reuse the adsorbent again, right? And even most of the paper, you have to show the reusability of your adsorbent after 10 times or 10 cycles, right? Then again, you have to keep that waste somewhere. I mean, it's important, right? Yeah, like for if you are removing some lead or something, finally you just get the lead, then you make some reaction, you make some process to remove the lead ions from the adsorbent and use the adsorbent one more again. The lead is waste. You have to keep. You have to put somewhere, or you have to to throw somewhere anyway, because it's a toxic material, right? But the issue in this case, to save the time and save the energy and to afford a very efficient way for recovery of precious metals, because all the metal in the world is good in some level and it will be toxic in higher level. So for example, iron is very important and we need it. Nickel, same. Copper, same. All this metal is same. Even uranium is also needed. But if the concentration of this metal ion increase over the permissible level, it will be toxic and it will enter to the food chain and it creates some serious problems to the people, human being. And sometimes also is the resources, the nickel and the metal, all the metal is the resources of the country. And if you just put it in the waste, then it will finish in some day. So you have to recover the precious one. So this is one of the most important way. It just use a flexible electrode from textile decorated with polypyrrole, then use it as electrode and absorb copper as a metal and the copper metal. Then after that, just burn the electrode decorated with the copper metal, then you will get the copper metal again. It's easier, and it's a good way to clean the water from the waste, from the metal, and also it's a green process. You just need the electricity circuit, simple, and also you get the copper, you get the materials, and you can sell out, you can do whatever you do, right? If you do that, then you have to characterize, first of all, the electrode. You have to show you have textiles, then you have a polypyrrole and so on. And after that, you have to show after absorption, after the process, after the actions, you have to show this is the copper atom have been absorbed, the copper ion have been reduced and absorbed as a copper atom on the surface of the electrode. You have to do that using scanning electron microscope, showing that, and you have to do with the edits. We talked yesterday about the edits, some elemental analysis. Yeah, there is, instead of all the element of the electrode composition, elemental composition, there is a copper exists. Okay, and the copper exists in the atom scale, state. And this is, the process of copper ion concentrations, because in this way also you have to optimize the procedure and so on. The other way, most of the people I told you there's a two branch of nanomaterial. Nanomaterial which is nano in the shape. That's why we call 0 dimension, 1 dimension, 2 dimension, 3 dimension, right? This is common everywhere, and the people using and using. But the other type of nanomaterial, which is nanomaterial inside, like nanoporous material, which have a nanoscale or nanoreactors, but inside the material. But the material will be bulk. If you see it will be macro scale, micro 2, micro 1, micro ion scale, or whatever. But inside there is some nanopore. And that's why I said advanced nanomaterial. And the people recently have been start to use that kind of material for different applications. Excuse me, I have to. Oh, okay. Okay, so the people just start nowadays to use such kind of this material for wastewater treatment. But the problem is initially the people use this material in organic, like silica, ordered silica, which is mesoporous material, and and it's expensive also, and they have to prepare from also silicate and so on, because it's not natural actually. You have to prepare from the beginning, and it's costly. Then simply the people start to use recycling of the biomass, reducing carbon, nanoporous carbon, and also they prepare in the beginning nanoporous carbon using template way. Just use the silica, order the silica, and they fill with carbon precursors. Then finally remove the carbon, the silica. Then they get nanoporous carbon, but they just nowadays the people start to recycling of the biomass. So in this paper, so you have to leave the phone. Okay, so in this case, in this paper, as examples, they use chicken feathers and they make recycling, washing, drying, carbonization. Then they get a porous carbon. Then they decorate, because when the people start or think to use a nanoporous material, they think to absorb the organic or inorganic pollutant on the pore of the nanoporous material, and this is physical absorption. Yeah, the chance is good after with steering or something. Yeah, the nano, if the dyes or if the metal ion size is smaller than the pore size, then it will go inside physically, and depends on the chance. But sometimes it will gone actually, because it's a bigger. So in order to make the post efficient, then polypiol layers, with polymeride on the surface of the porous material. Okay, then we finally get the nanopore, and the opening of the pore is decorated with some active site, which have a lone pair of electrons. Then it will attract and encore the positive charge dyes or metal ion, and they're forced to go inside the pores. This is very, very important. Okay, that's why I'm saying, if you are doing something, you have to sit down in your office or professor office and think much about the applications, what you're going to do, and design your material. It will take much time, not much time. It will take 1 month, 2 months, 3 months, even 6 months. But you will work smartly after that. Don't go to the lab directly. I want to work. I want to work. It's the hard working without mind is nothing. Is nothing. Okay. Yeah, this is IR and this is the XRD, and this is symbol, and most of you know about that. And this is the surface area. We the interesting things. Oh, sorry. The interesting things when we measure the surface area of the carbon only, the surface area was around 200 meters square per gram. But whenever we measure the surface area of the carbon decorated with polypyrrole, it's 4 times increase. It's around 800 meters square per gram. This means because the thin layers of polypyrrole, they created new pores on the surface. And also the pore diameter is around 2. It's mainly mesoporous material, and the pore volume is increased, and the material become very interesting actually, and very, very interesting. That's why when you are doing anything in your lab, and maybe the process become not good from your view, don't throw out. Go to your professor, knock to his office, and explain what you did and what's your material. All the discovery, most of the Nobel laureate, what the discovery comes by the mistake, actually comes by the mistake. But at the time they have a good student and they have a good postdoc When we have something wrong, they go to the professor office. Then professor office analyze, and professor analyze that one. Nobel Prize in chemistry in 2000, it comes by the mistake. The discovery of the magazine also, it comes by the chance. They was not going to develop magazine. Graphene, it comes by the chance, and Nobel Prize in Physics 2010. So most of this one comes by the chance. I mean, sometimes mistake, sometimes chance. Okay, it's very, very important. Whatever you do is valuable, but you should know what you have. Okay. Yeah, this is the factors, and we don't need to repeat about that, because I told you in this issue the design and the engineering of nano absorbent is the most important point in this issue. This is number of cycle, the usability of the materials, because in this case we use dyes. So see, after 10 cycles the efficiency is 85. It was initially 91, so 60% after 10 cycles. This is nothing. Then finally the mechanism. Did you see this slide number 28? You see, right?
Yes, sir.
Okay, so this is the mechanism. How it happens. The issue is very simple. You have a two approach. One approach is the dye, azidine dye, go inside the pore physically, or it encore in the positive active side of the polypure layer. So it comes by two mechanisms, and these two mechanisms achieve to maybe more than 90% removal efficiency. It's very important, I told you, to prove to the reader. That's the reader will understand. If you just, I actually, this is one of my paper actually. If we just explain that written, so the new student, the master student, or PhD student, maybe he will not understand fully. But if he sees the pictures, he read and sees the picture, he will fully understood what you are saying, and he will catch his idea. He will understand, and maybe it will trigger him or trigger her to develop something new. Okay. The other side, actually, nano photocatalyst. I don't know if any one of you working in photocatalyst or not, but this is another way of removal of organic pollutant. But in this way, it's not by absorption, it's by degradations. So here we are removing the toxicity, not the material. We are removing the toxicity, but not removing the material. This is why by photocatalytic degradations. What happens? What is the catalyst actually? The catalyst is something to remove, to accelerate the reactions. This is the catalyst actually. But photocatalyst means the catalyst will work based on the photon. So what is the issue? You need to have a semiconductor material like titanium, zinc oxide, iron oxide, cadmium sulfide, zinc sulfide. This is the main photocatalyst. So the idea is the light comes, in semiconductors there is a valence band and the conduction band. So photocatalyst is little bit, material science more. Means you have to have some physics background in a way. But it's already known, the mechanism already known. So, but the issue is to develop the new. This is the most important. And the process is similar. What I did here, you will do here, you will do there. It doesn't matter. So the issue is the electrons will come, or beam HNU. The photon will come from the sun, okay, or from the UV, whatever. And there's an energy gap in the semiconductors. Gap between valence band and the conduction band. Then the electrons will go from valence band to conduction band. Then it will leave a hole, and it will give in the conduction band electrons. The hole will be responsible to make oxidations of the water to oxygen radical and hydrogen positive, and also the electrons will be responsible to make reductions to the hydrogen radical and OH radical, oxygen radical. We say active oxygen species actually, We call all of this as an active oxygen species, and the active oxygen species actually was responsible for the degradations of the organic pollutant. But first of all, your organic pollutant have to be absorbed in the catalyst. That's why the catalyst should be have high surface area. This is very, very important. So in this case, you also have absorption. Okay, so you have to first of all, I'm just giving you the main idea, but I will go inside. Yeah, this is the mechanism actually. This is the mechanism. Titanium absorbs UV radiation from sunlight, produce pairs of electrons and holes. Electrons from valence band become excited when eliminated by light. Excess energy, blah blah blah, promoted the electron beam, the generation of negative electrons and positive hole species. That the hole and the positive hole, and this is responsible for oxidation of the water, actually reducing the OH radical and H positive, and the other one oxygen species and radical also, and all of this we call active oxygen species. It will go for the organic pollutant and degrade it to carbon dioxide and water. That's all. This is issue. But the problem is, nothing is easy. No, it's easy, right? No, there's some problem and some technical dilemma. And what the people doing? Otherwise, no need for do research. The problem is most of the semiconductors is working in have a big band gap, so it need a high energy, and then it's need UV rays, because when you see our sunlight gives UV range and visible range. The UV range is high energy, but from 190 until 270 is already filtrated by stratosphere, right? So in this, most of the research work now, they're using the UV lamp, right? Or they make engineering to band gap engineering using some bridge or something to narrow down or to just simulate some interlayer band gap to use the amount of energy. That's why we can shift to visible light. So to saving the time and saving the money, you have to use visible light. Visible light means low energy, means you have to narrow down the band gap. And this is a challenge actually, and there's many people just make some doping, they make some because this is the problem actually. So there's some chance they will be using cadmium selenide, cadmium sulfide in organic semiconductors. So this is the challenge actually. Using some modification, bulk modifications, using some graphene, some other materials to do that. This is one of also the most important for environmental applications, because this is just not only water, this is environmental applications and including water in the thin film actually. Slide number 33. Do you see now? 33.
Yes, sir.
So one of the most important things, before we know the water is toxic, we need to know the concentration of the heavy metal in water, right? Right? So you will imagine, yeah, this water is worse. No, we don't know. So first of all, we need a thin film. We need a thin film to sense, to measure the concentrations of. So the people use some big instrument, HPLC or ion chromatograph or something, and this is too much expensive. And maybe in your town, there's no any copy of ICB, for example, sometimes, because this instrument is very expensive actually. And but the people need to develop some portable electrode to because instead of to use portable electrode, you have to get the sample from the for example from the river or something, and go to the lab, take some 3-4 hours by the car, get the samples, and go here, and you take only one sample, so it takes much time. And the instrument need calibrations, and they're also expensive, need calibration, and give the operator, and the operator is not good, is not happy, then he will postpone the measurement. It's a crazy issue, right? But the people now start to think about using rapid and portable electrode. We could say ion selective electrode, just to detect the metal ion concentrations, just in 7 seconds, or even in 15 seconds. That's possible. The electrode it will. So nanomaterial play a very important role for developing the sensors which can sense rapid and accurate the concentration of the heavy metal or the concentration of the drugs in the water, because this is the first step before to characterize the water is waste or not. So this is very important. Now I think we finish the lecture 1. I will give you just 2 or 3 minutes until 10. Then we will. I think we have to enter again, right? Because the lecture has a time, right?
No, sir, I don't think so. You have to rejoin. I think we can continue with this one.
Okay, then it's fine. Okay, now we will just go for the pharmaceutical applications. All the people just think about the health. You see slide number 2, right?
Yes, sir.
Okay. A lot of before 2020 there was no any health crisis, just a simple issue. But after Corona, many people have been died over the world, and many people have been lost their job over the world, and the situation become too much crazy, and the people start to use the nanomaterials for different applications. This is the nanomaterial. I will skip this one because we have another energy, so still we need to talk about the energy, and this is the synthesis approach. We talk much about that, so we will not use much more. But this one is synthesis procedure. I told you about the top-down procedure of nanoparticles. First of all, we have to give some rules about the using of nanomaterial in medicine, for example. There are the 2 nanomaterial approaches or usage or exploitations. First of all, use in vitro means just you develop the textile to be antimicrobial or antiviral, for example, or you treat the surface, any surface, it doesn't matter, any surface, like mask, something, to be antimicrobial and antiviral. Okay, then it will not be inside the human body, right? So you don't care about the solubility, or you don't care about that. You just develop something should be compatible, because when any person just touches this one, it should not be hard. And this is very, but if you develop some vaccine which will comes, or antimicrobial material which comes take orally, then you have to care much about the solubility, and because it have to go through the serum, right? But outside the body, then not much care about the solubility of the materials. And many people working in, we could say engineering, but we could say medical applications or something. The people just start, and this has become now very, 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 very interesting route of research or trend of research, because the problems of the corona and the virus and so on. So most of the people try to to develop some emulsions, which is antimicrobial, antiviral, and they develop the textile and the surface and the wood and blah blah many things. But if you are going to use the materials for anti-cancer, for drug delivery, for antiviral, antimicrobial inside the body, then you have to think much more about the solubility or the dispersions of the materials. Because even if you do your work in vitro, not in vivo. Yeah, let me define first of all what's the meaning of in vitro and in vivo. In vitro, you are doing your experiment in clean bench, outside the body, the human body, okay? But you are doing some drug delivery or anti-cancer, whatever, but it's outside the body. It's in the lab. You just afford all the conditions similar like to lab, to human, but it's not in human, right? And you give the cancer cell and everything. But in vivo means you inject your drug or your material inside the any animal, like rabbit or something, any animal, any life animal anyway. Okay. So first of all, your nanomaterial. There's now two things you have to also care much. To use or to approve any material to be used as a drug, it will go through different steps. The first step is toxicity and is clinical tests and many things. But for research, the people doing research, whatever they like. So for research, I think most of you heard about Professor Mustafa Said. He's an Egyptian-American scientist. He developed 10 years back or something, or more than 20 years back, he just announced from the United States, he just discovered some very efficient anti-cancer drug by gold nanoroot. By gold nanoroot. Did you hear about that or not? Did you hear about that or not? I need the answer.
No, sir.
No? It's crazy. It's crazy. Anyway, maybe 20 years back, there's a professor, well-known professors. He's working in some university in the United States. He's called Mustafa Said, Professor Mustafa Said. By the way, he is the father of the metal nanoparticles. He just, when he was preparing in 27 or something, in 2007 or 2006, I don't know exactly, when he was preparing some metal nanoparticles, and he was preparing the gold nanoparticles. One of the characteristic issue for the metal nanoparticles is the surface plasma resonance, which we use UV visible to detect it. So he found out when he was preparing, he prepared some gold nanoroot by the chance also, gold nanoroot, because during the synthesis of gold nanoparticles, when you change the temperature, the shape will change. If you are preparing gold nanoparticles, when you change temperature and the condition, the shape of the nanoparticle will be changed, and the color will be changed, and the size will be changed. Then he discovered some gold nanoroot, and he found out the gold nanoroot has two plasma resonance. One plasma resonance at UV range at 500 something, and one in IR range. IR is very low energy. And he found that it's very important. When he just expose the solutions of gold nanoroot to IR rays or IR beam, it creates some photothermal. The temperature increased to 37 degrees centigrade. Then he tried to inject that gold nanoroot in some cancer cell and exposed to the IR ray. He found out very interesting. It's created heat, and the heat is 37 degrees centigrade, and make a photothermal degradations to the cancer cell. Then he tried to make antigen in the gold nanoroot. That's why the gold nanoroot, once you inject it, it will go directly to cancer cell only, and take the person, put in the tube, exposed to IR range. It will not be affect any organ in the body, but it will only stimulate the gold nanoroot to increase the temperature and to act the photothermal effect. And it was very interesting discovery at the times. and his son is working as a medical doctor in some university hospital in the United States, and they start to use different animal and so on. But till now, this drug is not validated to human. You know why? Because the gold nanowood is inorganic, and it will not be biodegraded. It will be still in the body of the human. So we don't know after 1 year, after 2 years, yeah, it's fine, it's biocompatible, but we don't know it's a change from its place, because after finishing the issue, all the gold nanowood will go to spleen or liver and it stays there. But we don't know after some times. Because it's inorganic material in our human body. So we save the person from the cancer, but we don't know what happens. So that's why for real applications and for real drug, the people used even nanomaterial, but biodegradable nanomaterials. Means they used like some polymeric material, polyethylene glycol, some polymeric material, polymeric nanoparticle like polyvinyl pyridine, not inorganic nanoparticle, I mean. But for research, you can do what you like. So for research, most of the people now, they use some silver, some gold, some iron magnetic nanoparticles, and some other material. Before you use you have two things. First of all, the size should not more than 250. You know why? Because if the size more than 250, it will not penetrate the cell membrane of the cell. Second thing, the material should be stable dispersion in aqueous solutions without any aggregation for at least 72 hours, because it should be the drug release time. So this is very important. That's why most of the people just go for water-soluble polymer or biodegradable polymer, because after as a drug delivery, but still some people using graphene, and including me also. I used graphene in 2017 as a drug carrier, but frankly speaking, if you want a new material, if you have develop some very interesting material and you make a patent and you have a dream that to be useful and to the material, to any other to these applications, it should be biocompatible, and after finishing the job, it should be gone from the body, right? So the people just go for the synthesis. And also, one of the most important things, if you are doing to pharmaceutical applications, you have to use material free of toxicity in the synthesis procedure. Like, for example, if you are preparing some polymer nanoparticle and you have to use organic solvent, so try to find the other way. Just use water. That's it. Or just use biocompatible material. Even comes from the nature, but don't use the toxic material, because it's not good. So this is the way, I think, of preparing polyvinyl pyridine using magnetic steering. I show you in the first lecture, second lecture, I don't know exactly, I don't remember, about the procedure of that, and we also show you this one, how to control everything. I don't need to repeat again, and also we show this one, we don't need to repeat this once again. But the issue, the new is, I used the polyvinyl pyridine nanoparticles as a tool to disperse the graphene, and then finally I used the graphene as an anti-cancer directly, and it was very interesting actually. All this experiment is in vitro, not in vivo. Okay. And this is a UV, because when you prepare the graphene, actually there's a bi-star peaks, which is at 280, from 260 to 280. If this exists, then you have a graphene sheets. Graphene. If this not exists, then you don't have graphene. You have something else. And whenever your absorption increase, means the number of graphene sheet in the colloidal solution is much higher. As this is, yesterday or the day before yesterday, I told you, in case of transmission electron microscope, we have a two carbon grade. One carbon is holy carbon only, I say, and one is holy carbon. Holy carbon is like what I show you right now. Is this one exactly? Is clear in in picture number D. Did you see slide number 10 right now?
Yes, sir.
Slide
It's 10.
Slide number 10.
Yes, sir.
Yes?
Yes, sir.
Yes, sir.
Okay, yes. So see the picture number D is a holy carbon, means it's like a network, and when you put your 2D material, it will be hanging and it will be much clearly, and you can see you can see transparent. Also picture number C, the graphene sheet is transparent actually, because it's hanging on the holy carbon. But in case of 0 dimensions, you have to use carbon only. But in all our country, we have only carbon only. In my country, for example, we have only carbon. We don't have a holy carbon. But for 2D and 1D, you have to use holy carbon grade. It will make much clearer to you to show your 2D material. Raman spectroscopy, of course, we have to do, and it's very important. No need to do. And this is, also the graphene sheet developed with polyethylene glycol nanoparticle, because also biodegradable. And you can see here, because whenever you use polymer nanoparticles and you put with graphite, then make ultrasonication, then makes centrifugations, then finally you will get this one. This again, these pictures I don't need to repeat again. Raman spectroscopy also is common, so I don't need to repeat. Anti-cancer activity. Yeah, now slide number 15, okay? You see, right?
Yes, sir.
Okay. So the initial evaluations of the anti-cancer activity of the materials you have actually is to do MTT, means to measure the cell viability. So if you develop some nanomaterials and you are gonna to use as an anti-cancer, or you're gonna use as a drug delivery, you have to give a proof of the biocompatibility of this material first. How? By just testing with the normal cell of the materials, right? So if the cell viability is more than 90%, then it's okay, then it's fine. Like in this case, we found out 5 hours, 16 hours. This is graphene sheet actually, but prepared with polymer nanoparticle steered at 16 hours. Polymer nanoparticle is steered at 24 hours. We found out 16 hours is the cell viability is around 70%. So we have to exclude this one. But the cell viability for 90% means this material is biocompatible with normal cell. That's why this is oriented drugs. If you have one of your relative or your network knowledge or something, and he using chemotherapy, actually, he has some many side effects, because the chemotherapy is not oriented to the cancer cell. The chemotherapy is attack normal cell and the cancer cell. That's why the research right now is directed to use oriented anti-cancer. And this is also the other cell is also, you can see here, it's most of them is more than 90% cell viability. And when you use the same cell but cancer cell of this cell, see, if you look to here at 100 milligram per liters, the dose. So you found out most of them is around 60% cell viability. In this case, this is a cancer cell. That's why we need to kill all the cancer cell. So we found out at 100 milligrams, 100 microgram. The issue is around 60%. But when we jump to 200, we have almost 90% killing of the cancer cell. And this is good. But this one is not good, because still for NIH3 T3 cells, cancer cell, so almost 40% is still cancer cell alive, and this is not good. The material is not efficient in this kind of cancer cell. Yeah, it's biocompatible, it's fine, it's good, but it's not efficient because still there is a 40% of the cancer cell, then we have to do treatment again, right? Another study, we just use polymer nanoparticles, and we exfoliate the graphene using polymer nanoparticles. And in this particular case, we just do, we just see experimentally the thickness of the graphene sheet, so it's around 4 nanometers, and we do Raman spectroscopy and everything, and we use the anti-cancer as and the drug delivery. So if you see here cell viability, or this one was different cell, it's the cell viability is almost more than 90% of the cancer cell have been killed actually, and also this one for the other different materials also have been killed actually, and we confirm that using microscope. By control and by 25 microgram per ml and till 200 microgram per ml. You find here in the picture number C, most of the cancer cell which is visible in the control is already destroyed, and this is confirmations of the efficiency of the anti-cancer. And also, in this work we have used graphene polymer nanoparticle doxops and used as a drug delivery systems. But in this particular case, we know very well the cancer cell pH. So we oriented our pH selective to be pH selective, means only the material will release the drug in much percentage in cancer cell only. So we found out at pH 5.2, which is acidic, little bit acidic, and the pH of the cancer cell more than 80% of the drug have been released after 4 days. But the problem is at 7.4 pH is nothing, is less than 20%. So this is the pH selective. That's why nowadays the people just use selective anti-cancer drug or selective drug delivery systems to avoid any side effect and also to increase the drug release. So our target to have a drug release 4 days instead of 1 day. Finally, I would like to also just to give hint about the other materials which is not inside the human body. It's outside, like antimicrobial, antiviral, and this kind of things. So the people try right now to develop some materials to use it on the textile to protect the textile surface or whatever the clothes we are wearing, or the curtain or our other furniture in a home, everywhere, even the chair of the car or something, to inhibit the growth of the bacteria and also to inhibit the growth of the virus once the virus fall down on these clothes. And this is one of the important research trend right now after the pandemic of coronavirus. People think much more about that because it's very important actually. The people actually in this initially like in this one, initially in this work we was using the metal nanoparticle like titanium like titanium dioxide nanoparticles, or just using some silver nanoparticles, but this is also toxic materials, and when you put your clothes in the washing machine, maybe some metal ion will be released after 1, 2, 3 cycle of washing. So the people think more and more to use biocompatible material but have some antimicrobial properties. And this work, the people use ketone nanoparticles alternating with casein, and using some biocompatible nanotubes like halocite nanotubes, which have antimicrobial properties, and showing different type of textile, and also measuring the durability, means the releasing of this one, and measuring after 5 cycles of washing what is the antimicrobial percentage and performance. And this is very important work. Now I will go to the energy lectures. Okay. So this is you see the slide number 2?
No, sir.
No?
No, sir.
Did you see the slides?
No, sir, till now.
No?
No, sir.
Did you see
Yes,
what?
sir. Now visible.
Visible. Okay, good. Okay. Slide number 2. You all right? You see now. It's visible.
Yes, sir. Slide number
Okay.
2.
Okay. So now we will just focus in energy, because energy is very, very important for most of the applications. So I will just take the branch based on my knowledge, actually, because energy, there is a production of energy. I'm working in solar cell, but solar cell, thermal energy solar cell. And I'm working also in the energy gases storage, like methane and hydrogen storage. There's some energy production, like even for solar in photovoltaic cell, and the people just using also some nanomaterial, barilla shape and so on. And also there's supercapacitors, the electrical charge storage. But I will just give some hint about the nanoporous material, which is used for supercapacitors, which is used for hydrogen and methane storage, and carbon dioxide captures, for examples. So this way we will just focus and why the nanomaterial is very important, why we use, for example, here nanoporous materials, and why, how to improve or to increase the surface area or the porosity and so on, to utilize this in proper way, because even in the storage and supercapacitors you need a porosity to facilitate the change or the movement of the electrons from here to there. And so the issue is the people just was using preparing some nanoporous material using different techniques, with different way, different something. But the problem is they don't care much about to use the nanomaterial as a shape. They prepare nanoporous material, but they didn't prepare nanomaterial, but also nanoporous material. Okay, so I will just give one example to you here, which is very important. Recently, the people just use a carbon, and if you have a filtration filter in your home, and you just take cartilage after the finish of the time of the cartilage and cut this cartilage, you will find the activated carbon actually black. So this one is activated carbon, and it's that's why the people just keep it in the cartilage back in the back systems, because it's it's not good for handling, and it's not good for using. And sometimes if you didn't change the cartilage, you will see some black particles in the water, but this is not good. And simply the many people, few people actually, including me, we think much more to use to make a much easier to handling the activated carbon. So we change to activated carbon cloth, which means you have a textile, but post textile from carbon materials, and to use for different applications. And instead of using a carbon as a fine powder, no, we use a carbon as a sheet, as a textile, and having surface area very much a high surface area. So here I will just I will not give much here. I will just give the picture, because it will be give senses. What we do here, we used exactly the nanoscale material to develop double safe nanopost material. Initially, we get the viscose rayon cloth. Then we make a polymerization of polypure nanoparticle of the surface. Then make carbonization. Then finally we make activation physically and chemically. Then we get some very interesting materials. And the problem is the polypure nanoparticles was changed to porous carbon nanoparticles, and the surface changed, the size changed. It was 150, it become 100 almost, but containing many pores. So we have a double C right now. We have a porous carbon nanoparticles decorated on the porous carbon textile, and this showing very, very interesting results. And even the carbon nanoparticle is rich with nitrogen. Then we have a very double active site exist in the porous materials. In order to improve why we use polypure nanoparticles here, is there for two reasons actually. The first reason is to enrich the material with a high electron density element, which is a nitrogen. Second things, to improve the gravitization process, because polypure has a good charring agent, so it will increase the charring agent of the materials. Third things, it will be enrich the porosity, because it will increase the porosity of the material, because polypure is very interesting material to afford high surface area materials. Okay. If you are just talking about carbon materials, then we have to give XRD of the material to see to characterize the material, because it's very important actually. And the powerful techniques, as I told you before, is Raman spectroscopy, and by evaluating the ratio between D band and G band, you easier know the quality of the material after activations, because this is also very important for many of the applications, to see what is the influence, or the harsh influence of the activations on the structure of the carbon materials. Yeah, this is morphological. I want to show you. This is very important. Yes. Yeah, this is very, very, very important. I told you before. If you have a nanomaterials, then you have to go for high magnification scanning electron microscope to confirm that you have nanomaterials. Actually, this paper is patent right now and is published in Chemical Engineering Journal in 2020. It's 15 impact factors. So because it was new and it was really patent, and many people right now cite us and using our approach actually. You know now A and B is just the surface area of the just textile viscose without anything, but C and D is a carbon actually activated one. When you just enlarge, you want to see the particle, the carbon nanoporous carbon material decorated on the carbon sheet. You will see it's almost is spherical shape, and whenever you increase the activation conditions, you can see the harsh of the topography of the nanoparticle have been changed because the concentration of the activating agent become much higher. And also it's important to see the elemental analysis using ADX or EDS, whatever, same name. So we have a carbon and oxygen, nitrogen, chlor, zinc. So why it comes from? Because during the process, why chlor and zinc comes from? Actually, zinc comes because before make activations, we have to immerse the material in ammonium chloride and zinc chloride to enrich the charring process. Otherwise, you will not get any carbon from the combustion of the after carbonizations of the textile. And zinc comes from the residue, and also chlor comes from the residue because after activation we have to wash with 10% HCl. But nitrogen comes from the polypyrrole nanoparticle, which is converted to porous carbon nanoparticles, and oxygen comes from the same. So this is very important. Yeah, this is a texture properties. I will just show you here because this is very important actually. You have to know the surface area. You have to know the both side distributions. You have to know what you have exactly, because this is the based on the results you get. You will define your material will have a good performance in the hydrogen uptake, carbon dioxide capture or not. So in this case, the surface area of the much more material is more than around almost near to 2,000 meters square per gram, and we found out we have a hierarchical bore structures. What does it mean of hierarchical? We have a microbore and mesobore of the bores. So the distribution of the bore of the map of the porosity is between microbore and mesobore, means hierarchical structure, and this is very, very important in the hydrogen uptake and the methane uptake, because at lower pressure you can just store your material in the small bore, and at high pressure you need a much higher bore size. You can store the other things in the large at high pressure. And this is the surface area of the material, and this is the bore diameter and the solution of the materials. You can see here very easier, almost 1911. You can see almost 2,000 meters square per gram, and this very interesting results actually. Hydrogen storage data actually. This is one of the most important things to do. This is we have to do excess hydrogen uptake capacity at room temperature, and we have to do at ambient temperature. Actually, the real application is to do at ambient temperature, but because of this is still in this way the hydrogen is stored as stored on the surface of the material by weak interaction bond between the hydrogen molecule and the absorbent surface, and it absorbs much higher at 77 Kelvin, but when you increase temperature to room temperature, the thermal motion will provoke the weak bond between the hydrogen molecule and the adsorbent. That's why still technical dilemma and challenge for the people working in hydrogen storage materials to achieve good uptake at ambient temperature. This is the results actually for this one. You can reach 4 weight percent and around 0.2% at ambient temperature. Now I think we finish the course. I know there is still electronic application we didn't do, but we don't have time actually because this need much more time each lectures, because this course I think I give it. There's other two applications actually, environmental applications and electronic applications, and both of you, each one need at least 1.5 hours to give just overview, just a few papers actually to explain the basics and to explain some publications. Because the time is short, every time we just have only 1 hour, and this is not enough actually. I hope you understand some of the knowledge during the last 5 days, and I hope I open some window in your mind, because knowledge you can get it everywhere, no problem. But the problem is the guidance which I give to you, and the philosophy which I share with you, and the orientations which I did during this last 5 days to you. So I'm just giving my experience to you. I'm sharing my experience with you. I'm not just giving some knowledge because it's easier. You can get it everywhere. It's not much. I mean, you can do, but any training everywhere, even the course you are taking in the undergrad or postgrad, you're just opening the door for you. And if you wanna learn more, you can just go for more. I hope you just understood some of the facts about which you don't know, because I don't know the classifications or the map of your educations. Maybe undergrad or just graduated, he learned much. Maybe some people is mature and know what I did or what I say during the last 5 days. Maybe some of you didn't understand many things. Also, sometimes happens. Finally, I pray for all of you to the best, and I'm ready to answer questions. Actually, I tried to give some times for the questions, because yesterday also some of you need to ask some questions. So you have around 15 minutes to ask questions, and I answer you, and to ask whatever you like. And if I know the answer, I will definitely answer you. If I don't know, I will tell you I don't know. Okay.
Yes, sir.
Okay. Any questions?
Yes, sir, please.
Yeah. What's your question? What?
And this PDF, sir, move towards slide number 6, please.
What?
And this PDF move towards slide number 6.
Which slide?
And this PDF, slide number 6.
Excuse me, Akhtar.
Yes.
I didn't get your point, Akhtar. What you need? What you are saying?
My voice is not clear to you people.
There's some, your voice is not clear, Akhtar, to me. Your voice, there's some noise. Some noise.
Akhtar, kindly ask your questions after Dr. Adnan Rauf closing remarks. Please be patient.
Okay, ma'am. Okay, thank you.
Ladies and gentlemen, I would like to invite Director IM Group of Researchers, Dr. Adnan Rauf, for closing remarks. Dr. Adnan is an Assistant Professor of Material and Analytical Chemistry at University of Savat. His PhD in Analytical Chemistry is from University of Peshawar. He has done his PhD research from Columbia University, NY, USA. His research expertise are alternate energy production, energy storage and water splitting reactions, heterogeneous catalysis, waste valuable chemical and fuels, nano-size particle technology, removal of heavy metals, dyes and toxicants from the aqueous media. He has published several papers in prestigious journals such as Journal of Molecular Structure, Coordination Chemistry Reviews, Journal of Industrial Engineering Chemistry, Journal of Taiwan Institute of Chemical Engineers, Journal of Analytical and Applied Pyrolysis and Process Safety and Environmental Protection. Dear sir, welcome.
Thank you, Safia. First of all, I have to tell you about some about the course. This course, Nanoscience and Nanotechnology, is very important and aligned with the modern needs. Nanotechnology finds application in medicines, targeted drug delivery, and in electronics, producing smaller and more efficient devices. It also contributes to the environmental solutions such as water purification and energy generation. In fact, one cannot imagine the world without nanotechnology. And I think this ending remarks time is very less. I suggest that Dr. Noor Atia will have presented well the applications of nanoscience and nanotechnology. As we wrap up this nanoscience and nanotechnology course, so I would like to extend from my side and from my team heartfelt thanks to Professor Noor F. Atia for sharing his valuable expertise, making the learning experience truly insightful. Then I have a big shout out to the course organizers for their hard work and putting this together. And a special thanks to all of the participants who joined us. Your active participation has made this journey engaging and rewarding. Let's take the knowledge gained here to inspire new innovations and make a positive impact in our fields. Thank you once again, all of you.
Okay. Okay. Thank you.
Thank you, dear sir. Dear participants, now you can clear your doubts. Fatma, I think you have a question.
Ma'am, sir is online, or I think he left.
Yes, he is online, I think so.
Excuse me, sir.
Okay.
Sir?
Yes, yes, yes. Tell me what you have.
Okay, sir, actually this thing really irritates my understanding. We usually say that chemical and physical property of material changes at nanoscales dramatically. Why it do happens? Like why they change dramatically at nanoscale?
Yeah, it's a good question actually.
मतलब
Actually,
आंटी और
because
है आंटी ने कल कहा था मैं आऊंगी ये सारे बर्तन मैंने आए मैं छोड़ूंगी
okay, excuse me. Actually, the physical and the chemical properties change because you change the dimension of the nanomaterial. Like, for example, I will tell you some examples. For 2D material, actually, when you have graphite, for example, the graphite is a soft material, right? We call it soft, solid lubricant. And the graphite is not electrical conductive, is, you can say, semiconductor. But when you exfoliate the graphite to graphene, the thickness of the sheet is around 1 nanometer, right? And the mechanical properties become much higher, and because the surface area become much higher, and the electrical conductivity become much higher, because you change the state of the materials. So because surface area have been changed, so definitely there's something known, actually, but because you change the structure. Like for graphite, for example, the graphite is a stacked layer from graphene, right? But you exfoliate individual sheet. Surface area will be 2,000 meters square, 2,600 meters square. First of all, the graphite itself, it will be 10 meters square per gram, but the single layer of graphene is 2,620 meters square per gram. And the mechanical, for example, tensile strength of the single layer of graphene maybe 100 times more than the metal, for example, and steel, for example, stainless steel. And the electrical conductivity have been increased because the thickness of the sheet is 1 nanometer, but the thickness of the graphite sheet is like 3 or 2, from 2 to 3 micrometer, right? So dimension change, then the movement of the electrons, it will be changed. Like, for example, like surface plasma resonance for nanoparticles. If you have a silver or if you have a gold at macro scale, then there's no surface plasma resonance. But when you change and you change the physical the dimension to nanoscale, then you will get surface plasma resonance. You don't know what's the meaning of surface plasma resonance. Surface plasma resonance means there's a free movement of the electrons, because the size of the nanoparticle is much smaller, so there is a free movement of the electrons around the atoms. So this is actually the reasons why the physical and the chemical and everything change, because surface area change and everything change, dimension change. Then new features have been created on the surface. I hope my answer was much clear to you. Any questions or comment? And one more thing. Okay, one more thing I would like to also to tell you, actually. You know, even the optical properties change. For example, if you have a gold, for example, the silver at macro scale is white, right? Is white in color almost. But when you go for nanoscale, it's become yellowish, right? Because everything changed, actually. Any questions or comment?
Yes, Amara, you can ask.
Amara Aslam. Okay, tell me what you have. Somebody else. Amara Aslam is still hesitating.
Sir, there is one question in the text.
Somebody say if you change material to nanoscience, it's electronic. Yeah, not electronic actually much, but it's the geometric structure, but also geometric structure is not changed actually, because the for example, for the graphene, for example, we didn't change the geometric structure of graphene. Graphene is 6 carbon and stacked. So you change the other dimensions, and this is very important, and that's why the electronic and the movement of the electron will be changed. and this will be affected in the robotics. But for example, the mechanical also become much more important. So, and the surface area become much more. So change, it depends from material to materials, but most of the material, the geometric structure is not changed actually, because if you have a titanium dioxide in the structure in macro scale, and you have titanium dioxide nanoscale, X are the same. Zinc oxide and zinc oxide nanoparticle, X are the same because unit cell is the same. You cannot change, right? Anyway, some other questions?
So, if we change like zinc oxide in nanoparticle side, it means its electronic structure must be changed, like D band.
No. Electronic structure, yeah, it's changed. But I mean, I'm asking about the geometric, the unit cell of the materials. It will not be changed actually, because I will tell you something very important. We in the nanomaterial approach, listen carefully to what I'm saying. In nanomaterial approach, there is a top down and bottom up. In the case of top down, even I do in my lab, we prepare titanium dioxide nanoparticles from titanium dioxide scales. So we measure the IR, we measure the XRD for the both. There's no change. Only what the change is the dimension, and after dimension change, the other chemical properties change. But the main things doesn't change actually. And if the change, then you change the material at all. Okay. Try in your lab. Try to prepare some zinc oxide from using ball milling, for example, and measure IR and measure XRD for the material before and after. But if you measure thermal analysis, it will be improved. It depends actually from material to material. Anyway, any questions or comment? Okay, if this is not the case, I would like to thank all of you for your active listening, and have a good day. And I hope my effort with you during the last 5 days or 6 days have enriched your knowledge and have orient you, and maybe some of you have some mistakes here now we have to correct. And have a good day, and bye-bye. Assalamu alaikum.
Thank you, sir. So, ladies and gentlemen, first and foremost, I want to thank our instructor for his unwavering dedication and commitment to our growth and development throughout this course. His passion for teaching and his ability to communicate complex concepts with clarity and simplicity have truly made a significant impact on our learning experience. Furthermore, I would like to express my gratitude for the innovative and engaging teaching methods of our instructor. Thank you so very much for your patience and empathy, dear sir. At the end, I would like to pay gratitude to the entire team of IM Group of Researchers for organizing such a great course. Thank you, dear participants, for your active participation. Thank you, everyone. Thank you so much. Take care and Allah Hafiz.